Thank you very much. Thanks to be here for the little anecdote. It's my first talk in my life, so just enjoy it, please. We will talk about some modern electronic lockpicking. It's quite pretentious, I agree with you, but you will see it will be really fun. We will talk about some physical design vulnerability. Of course, I have confirmed it with another device. And after, we have a big part about Bluetooth Low Energy, which because it's my favorite color of money, and you will see why. So, of course, let's go. I'm a senior security auditor for Orange Cyber Defense since 2017. I work in Rennes, in France. I like IoT and especially hardware and reverse things since 2-3 years ago. I'm an ex-CTF player, so I'm quite old now. I can't bypass a full night. I'm quite old. So, before to discuss about some smart lock, let's go back several thousand years. Little history. According to the historians, trace of the first lock, as we know, that back to the ancient Egypt. The design is really easy, just only 3 pins. The material, it's easy to break, of course, just wood. But this design, it's currently already used, but of course with more pins, more secure material like steel and other things. In 1951, there was this great lock controversy. A famous lock manufacturer from United States, Mr. Hobbs, picked Chubb's lock, which is an unbreakable lock for 60 years. During the Great Exposition at London. So, of course, at this epoch, it was he breaks the unbreakable lock, and the same year he breaks to the Braham lock, which is another unbreakable lock. Of course, in the last 30 years, many technology evolving. For example, we have Bluetooth Low Energy in 2009. Of course, we have Zigbee, we have Wi-Fi, and everything. So all of it create a lot of hacking possibility for us. So yes, there are already some hacking story in about smart locks in DevCon or Black Hat conference, but I think we can find some other conferences like in Insomniac too. So the physical vulnerability. Obviously, a lock must protect the access from unwanted people. You can always use the brute force attack to break the door and enter to the house or to the room, but we will don't do that in this talk. We want to be like James Bond. Maybe we can have some tools just open the door for us. Yes, let's see. So, of course, when we talk about physical, we have to find a physical entry to attack the hardware. And once you are in the hardware, you have to understand how the lock works, how is there many boards inside the lock, how boards communicate with them, both together. And obviously, if we can get the hardware, we will try to reverse the firmware if we can get it. To find password, hidden functionality, backdoor, vulnerability like buffer overflow or everything. So this is the lock. So sorry, but I don't disclose any name of company during this talk due to some respect. You will see why before. Not for the lock manufacturer, because for lock manufacturer, sorry, but I have no pity for them. But for the BLE creator, it was really great. So just for them, I will not disclose any name on this talk. So we have this this lock, which is quite simple. We have 3 parts, 2 big parts. One are outside of the house. The outside has the main board, has the battery, of course, outside. If the power is off, you can change the battery easily. And inside the cylinder, inside the door, you can find a motherboard in this talk. So, of course, let's dig in a little on this board. So first, the main board has a Nordic processor, ARM Cortex, M4 32 bits. Sorry. We can find some other motor controller on this board. Of course, we have a connector because of course the main board has to communicate with the motherboard, so we have to communicate with them, and they choose a wire connection. And we can find some pin on this board. So sorry, I have already soldered them because first I don't think that my work I will bring me here just in front of you. So on the motherboard connector, we can find the whole pin about debug. So we will use them a little bit later. Same thing for the motherboard. We have a microcontroller, of course. It's a STM8. We have another motor controller. We have the motherboard connector, of course. And some other debug port. We can find a UART connector. So the thing is that the TX is working, RX doesn't work. The debug connector is used, but I can't find anything on this pin. Well, for this board, they have to do the right thing. So, of course, we have to find a physical entry point. So, when you are in front of the lock, once you remove the stainless protector, you have a little pellet. You can really easy to remove it. Just drill it, and you remove it, and we have access to the motor connector. Really easy. So that's it. We can have access to the connector between the main board and the motherboard. Of course, they forget to remove read protection on the processor of the main board. So we can connect them. We can connect to it with OpenOCD, and we can extract the firmware. And we can put the firmware that we try. We can use an NRF ident, which is an open source program, to identify the Nordic SDK version. Obviously, you can connect GDB. It's easily for us. It's more easily to use GDB to extract some part of memory, like RAM, like pin configuration, and everything. So first, they don't hide any information about the hardware. So thanks for that. It's easy for us to retrieve datasheet on the web. Electronic board is not difficult. It's really easy to access to it. Debug port is not deactivated, and weak protection of the processor is not set. Okay, thank you very much. So, of course, I said that we have the motor connection access. So let's use a logical analyzer to see what's going on the wire. I don't connect the red wire because red wire is only power. So we run our logical analyzer. We have this channel. Let's dig it. We have 3 parts. The first in blue is probably just a wake up signal to the motherboard. We have 2 other big parts. Probably the request and the response from the motherboard. So let's zoom on the first one. Okay. Here we can see that we don't have many symbols. We can see that we have only 2 symbols during on the signal. So let's do an exception. Okay, we have a 0, we have a 1. Because for me, I don't like play with it. Personally, I prefer string, so I prefer hexadecimal. It will be easier for me if I can treat the data with hexadecimal string. And once you have the language, the hexadecimal conversion, to analyze the communication, I take sample at different action, of course, during the initialization. So initialization is when you power on the lock. So you remove the battery and you put the battery back. It's the initialization. And the opening is, of course, when you enter the right code or you use your phone, the lock is open. So this is the function. I take 2 different controllers, C1, C2. And obviously, at 2 different times, the -1, -2. So of course, we can say that we don't have any time issue, any time token. So we can probably do a replay attack of that, obviously. So let's go deeper. We have some few bytes we never change. So okay. The first one is maybe some headers. The other is some maybe separator. We have a byte we change only during the function. So for initialization, we have in ping part we have 3, and opening during opening we have 1. So this is the command byte. Okay. And of course we have a big part in middle in orange, which is maybe I know it's at the ID of the motherboard, but it's maybe some an ID. And the first is just a checksum. If you don't trust me, you can check it just with the command, because you can see on the first line that you have 87 with 3 command, and on the opening function you have 95, and you have one in command. So it's maybe a checksum. So of course, communication is unencrypted, is not signed. They don't have any protection against triple attack, and of course, yes, they seem use sensitive data without authentication, because when you put the battery back, sorry, but this is not an authentication. Yes, you tried. Okay. Okay, so this is the easy part. Let's go deeper on the firmwares. First of all, before attack the firmware, I have to extract, obviously, all the part of the processor. With the datasheet, we have all addresses that we want, so we can extract the pin configuration, we can extract the RAM memory, and everything. Of course, the first thing you do when you have a binary is just do a string. It's a basic. We have some string on result. Some of them are can be interesting. Dynamic password, yes, why not? We have some string which looks like some identifier or some token maybe, and obviously we have some file path and GitHub command, GitHub URL, of course. Thanks for that. Thank you, developers. First of all, I will focus on the EF40 and the KV40 because for me it's quite strange. They came really a lot, so it's maybe some magic number. So I look for EasyFlash. EasyFlash, it's an open source project to manage memory on bare metal firmware. So let's go on the source code of EasyFlash. Thanks to GitHub, we have some. Obviously, we have some structure. We have some function. So let's go find this function and structure inside our firmware. Okay, so we have the create env blob. Once we have the function to manage the blob, you can follow all the call stack to find the memory which is modified, read, written, and we find a memory like that. So we find the KV40, we find some probably CRC32, we find the lanes, name lanes, and everything, and we can find the name. Here it's lots settings. Okay, well, I love Ghidra, but I'm really bad to create some plugin on Ghidra, so I prefer to take my Python script. So I write a Python script to search for me all of the data which follows the structure of the EasyFlash project. I found 60 structure, and some of them are really interesting, like log setting, of course, and hard ID. Yes, because the first log is obviously I have put a very strong password on it, which is 1, 2, 3, 4, 5, 6. Very strong. Don't use it, please. So the password is really in plain text. We use it. We can use it. We can find it really easily. So I don't speak about it, but we have a master password which never change. You can reset the log, but the master password doesn't change. It's like a joker. If you forget your code, you can reset the log. Maybe you can think that the master password is random. Well, no. It's why use random when you can just increment it? It's more easier to increment than do random. Okay. So you can read some of them, and if you know the time when your target bought his lock, you probably can reduce the brute forcing part of the master password. So obviously, passwords are not hashed, master passwords are not random. Okay, thanks for that too. So let's go deeper in the firmware, of course. So here we have found the password. We have to find the command implementation. So to do that, I use the ID because as I have extracted the RAM memory, I can search in the RAM memory for the ID. Obviously, the ID must come from somewhere. So we have just follow the call stack and the reference, external reference to the memory address. The first of all is obviously the write. So the ID comes from a FICR register. So it's a full random 8-byte identifier for each Nordic processor. It's set in factory, you can't modify it, and it's fully random. Well, okay, this is quite good. Okay, we have only one place that the data is read. Okay, let's go. So we have our function, launch motor command. Obviously, I have renamed it. And we have 3 positions in the code where we call this function. You have it here. So obviously, we have the open command, we have the initialization command, and we have the last one, but I can't say anything on it because I don't have success to trigger it. Maybe I have tried, but maybe it's some one-shot command to initialize the motor board with the identifier of the main board when the lock is in factory. So obviously here we have firmware, we have the communication language, we have everything that we know, everything that we have to do to create an attack card. But I don't want to create an attack card because even if I like Raspberry Pi or Arduino, I want to save the planet and I just want to reuse my main board tested card. So I take the firmware and I put my code inside the firmware. Why I do that? Because you can say, well, you have the debug port, you can flash all the firmware. Well, I don't reverse everything in that firmware because reversing a bare metal firmware, it's quite complicated for me. And it's quite time consuming a lot. So I don't want to waste too much time on the initialization reverse. So like that, I can use all the initialization of the firmware of the constructor. Okay, perfect. So I put just my command, my code inside the firmware. Because I have the size to do it, because the firmware is not full, it doesn't take the full place, doesn't take the full memory of the processor. So, of course, you can find here some of my attack code. So we have to intercept the ID. So we transform, we switch our card like obviously a logical analyzer. And once we have the identifier, we adjust to send the open command to the lock. And obviously, I have built a door lock. I have built a little door to show my work. No. Ah, demo effect. So let's go. So we have. This attack can be done on the real door, of course. It's absolutely not mandatory to be in laboratory. So we pull back the battery. We wait for the initialization command. Here I have read the identifier, and here I have opened the door. In less in that 8 seconds. So yes, of course, you can add it because I disable the sound, but we can hear the little door, the little motor inside the door. So in 8 seconds, I can open your door. Okay, that is for one lock, but this design is used in many other type of lock. So I take another one lock of the manufacturer. Obviously not the same lock. Okay, so I took this one with a fingerprinting captor and with NFC possibility to open the door. The connector is easily accessible. It's just turned by 90 degrees, but you can use it. You can always use it. We can find obviously debug port. So okay. So let's go analyze the communication between the motor on the main board. So we are only one wire to data. And here, they don't implement any specific constructor communication. That is the protocol. They just use a UART classical, but they use in one wire. So they switch the RX and TX, the receive and transmission, on the wire between request and answer. Okay, so it's best for me because I don't have to return a specific plugin to extract the data. Okay, we find the same structure, command, ID. Okay, perfect. Let's go with opening because of course this is for initialization. So just when you pull back the battery, and for opening this is the same. Thanks for that. We have the same design. So obviously, I have to check, of course, the read protection. Well, they set it. Bad luck. But no. Thanks to include security in Cortex M0, there are a vulnerability which affects all of Nordic NRF 51, because yes, the board doesn't have the same processor of the first lock, and thanks to that, we can read register and we can set register, but obviously in the few steps of the initialization, a processor just read one address of the memory. Okay, so we have just to put the address what we want to read and just step 1, and obviously we have the result in the register. This is for the vulnerability. So thanks to that, you can extract the firmware, you can dump the firmware in 20 minutes for 2056 kilobytes. So it's quite fast. So I have reversed the firmware too, but yes, I just want to confirm how commands are implemented. So of course we have the same problem. Communication is unencrypted, USIGN, no protection against replay attack, and they use sensitive data without authentication. Thanks. For it, I don't have make a specific attack board. The most easy part is just to hard code the identifier on the inside the firmware, and you just put all command like initialization, open, everything. You hard code the fact that all command is just opening function. So you just have to put your attack card and it opens the door. Of course, there are NFC, so I have to do check it. First of all, without any administrator, any MFC card can open the door. Thanks for that. Obviously, the documentation of the log says you have to set an administrator. But I'm sure that we can find some log without administrator in the wild. And with administrator, maybe it's better. Absolutely not, because in the memory, they are just the UID of NFC tag inside the memory. So of course, they don't use a secure, if NFC can be secured, behavior. Thanks for that. Please don't use UID to authenticate people with NFC card, please. Okay, so here I have done the full physical vulnerability. We will talk about Bluetooth low energy. So for the first logs, they use a SDK provided by a specialized company in the Internet of Things world. They have cloud integration. It's a major actor in IoT world. They don't use any encryption protocol. protocol encryption. It's a full plain text Bluetooth low energy communication. But they have implemented some encryption on the software side. They just use Bluetooth like a raw wire. Okay, so we can find maybe the IV, and we have a packet, but only for 20 bytes length. So we have a counter to say the packet is the 4th packet, the 5th packet. Okay. Let's go do some free hooking with objection open source program. Well, you hook on the IES function. So as you can find the key, you can find the initialization vector and everything. Okay, you can print the stack trace too. It's easier for us to get the call trace, to do reverse. So, of course, I have done two trace, and I compare the key. The first key are always the same, always. But the other change. Okay, so maybe they have to exchange some random token or something to change the key. Okay, why not? But the most interesting part is that the key is always the same. Okay, keep that in mind. Obviously, even if I like Frida, when developer put log inside their code and give us the possibility to put the switcher, the log back, yes, just use it. So there are two functions which is called secret key 4, secret key 5. So obviously it's quite, it's not really easy to read. So just focus on the green and the orange packet boxes. It's much easier like that. So the first key is just MD5 checksum of the login key, and the second key is a MD5 checksum from the concatenation of the login key plus S1. Okay. Thanks to logcat, we have the size of the login key, we have the srand, and here we have the first critical problem. The login key is only 6 hexadecimal characters. Thanks for that, because obviously 6 character in hexadecimal is really easy to crack. So we will just focus on the first packet. So the first and the second packet between the mobile and the device. So on the device, so the first request doesn't have any specific strings, but the device respond to us with many information. First, we found we have the hotkey, we have a device ID, and we have the S1. So we don't have to brute force the S1. The second request, it's more interesting from the mobile part. On the device, it just maybe okay, you just bad. So on the request, on the mobile part, we have the device ID, we have the login key, and here we have the UUID. Well, but I don't pick for UUID. Okay, just let's find where is the UUID. Each Bluetooth device has some advertising communication which broadcasts every time. Once it's power on, it broadcasts some data. In the data of the lock, we can find the UID, which is encrypted by AES CBC with a key. The key is given to us with the advertisement data. Okay, so just do that. But where come from the IS key? It just come from here, and thanks for them, it's the IS key they use, the half of the IS key, is the UID encrypted by login key and UID. But you know UID, you just have to guess the login key. You know the plain text, you know the ciphertext, you know a part of the key. You just have to brute force 6 hexadecimal character. Thanks. No, so obviously they don't use any Bluetooth low energy encryption. They can be used. But no, even if you use MD5 checksum, your IS key is not 60 byte length. The chart set of the key is not large at all, and obviously don't use sensible data to generate public data in a secure way. So here, maybe I can do something with that. So we have USDK. Obviously, the mandatory part is that an inbound device should not be able to communicate with the device. If you bound your phone, only your phone on your account on the SDK cloud integration can communicate with the lock or with the device. But we have two vulnerability. We have a 6-character string. We have the same string is used to create sensible, accessible data. Okay, so we can have a decryption of all communication on the fly or offline, as you want. And obviously, we can interact of a device without any user or cloud interaction. Thank you for that. So, of course, I have done some responsible disclosure, but just go to 2 steps to weaponize it. So, the first is optimize the brute force algorithm thanks hashcat. Find some Bluetooth parameter, analyze an open and check, or whatever, or the request that you want implemented in your client. And obviously, Open Sesame. I will not release the script, but I will show you. So I'm quite late, so I will advance a lot. So we have to pair. Obviously, we have to pair our phone with the lock. So thanks to that, okay, we can open, and when we open the door with the application, we have a log. We have a log inside the application. Okay, so let's go the attack. So here I have found the login key. I brute force the login key, of course. I have found it, and once you found it, you have everything, every string, because log sent to them. So you sent to you. So you can use it to open the door. So in less than 20 seconds, I can open the lock only with that. And obviously, no log at all inside the application. I have confirmed the vulnerability with another device. Oop. Voilà, so it's just a little drawer. It's the same vulnerability, and in a few seconds, I can open it. So the vulnerability doesn't affect only one device; it affects all devices with the Bluetooth SDK. Okay, sorry, I know my talk is long. Sorry about that. So, of course, I have tried to do a responsible disclosure for the physical vulnerability. So they don't really take me in consideration. You will say, yes, of course, it's a Chinese company. Yes, okay. So I came back in September about Bluetooth vulnerability, and then said to me, go to the police station. Okay, yes, but I just want to say that you have a vulnerability. I don't want the police station. Okay. The most fun part on the manufacturer is that you have they have a blog obviously, where they talk about security of connected lock. So thanks, but we can do some Bluetooth attack, we can do replay attack and physical attack. It's possible on your lock. Thanks for that. I quite finished. So for the BLE SDK creator, I have failed to found their multi-platform on the SecMail. The customer support doesn't trust me in September, but thanks for me and for them, it was much better in February. So you can have you have the timeline on the screen. So they was really great. I want to say thank you to them because they authorized me to give the talk despite of the critical vulnerability, and they paid me the reward, and I have the maximum reward of their Bounty platform. So really thanks. It was a very great exchange. So for manufacturer, of course, please use best practice, listen security researcher. And for you, sorry, I don't have any solution, perfect solution. If you want to choose some smart object, well, do your own research, do it for reputation or anything. I don't have a perfect solution for that, sorry. Thanks for your listening.
Okay, we have a little bit more than 3 minutes for questions. Any raised hands?
Thank you for the talk. On the first part, how much time do you need to drill the hole and do all the necessary steps to plug your attack card or plug your stuff to opponent?
To drill the pellet?
Sorry?
To drill the pellet?
Yes, to connect your attack. Well, it wasn't an attack card. But
in 2 minutes, I think, on the door.
So 2 minutes plus the time, was I don't know, 5-10 seconds, and 3 minutes you're in. Okay, awesome.
Of course, the pellet, you have to replace it. So you just buy the same lock on your e-commerce website and just put glue and replace a new pellet, of course. Because if you make a hole, you can see the hole.
No more questions? Okay. Thank you, Thomas. Very good presentation.
Thank you. Thank you.
A round of applause for you.